All right. Can everyone hear me okay? Just. All right. Can everyone hear me okay? Okay, there we go. All right. Hi, everyone. My name is Aaron Allen. I'm on the Haskell.org committee. I also write Haskell professionally for a company called HEB. So, as you may know, Haskell has a long-standing and successful presence in the Google Summer of Code program. Unfortunately, this year we weren't accepted into Google Summer of Code, but we wanted to keep that momentum going from previous years, so the Summer of Haskell 2023 was born. And I'd also like to give a shout out to David Christensen, Gershom Baserman, and Jasper Vandershoot for assisting and organizing and running this event. And a huge thank you to the sponsors who provided financial backing that made this possible. So here we have a list of all of the participants. So each contributor has a project and a mentor that they worked with in order to hack on something that would provide benefit to the ecosystem. And the bulk of this presentation is going to be the contributors explaining their projects and showing some of the results. So without further ado, let's get into that. First up, we have Ben Bellick.
Hear me? Cool. All right, so today I'm talking about rendering GHC diagnostics as JSON. As Aaron just said, I'm Ben Bellick. Just a little bit about me. I got selected for Summer of Haskell. I was really excited to contribute to GHC this summer, so this has been a great opportunity for myself. So let's get started. So today I'm talking about a new feature that I'm trying to help bring to GHC, which is a flag that helps make GHC's diagnostics more easily readable by a machine. So to put this in another way, let's make GHC's diagnostics available for everyone, regardless of what platform, what tools they're using. We should make sure it's easy to consume. So let's see an example just to get a flavor of what this particular flag is going to do. So this is, I'm sure, recognizable to everyone, an error output by GHC. And you can see it's got a lot of great info inside of it, but it's a terrible pain to parse by hand. And to make matters worse, the actual output can change between releases. So for example, some people might be familiar with, can you see, yeah, with this code here, and some people might not. It's something that's being rolled out in real time to basically add error codes to all the possible errors to GHC. If you wrote a tool that was parsing this information by hand and suddenly that came up in a new release, boom, that's a big issue, right? All of a sudden you have to rewrite your parser by hand again. So how can we make this easier for people to consume? We represent it as JSON. So now all of the information that you actually want is available in its own individual field. And this is hugely beneficial because now who cares if a new field pops up when you're not expecting one, as long as this format stays consistent. So why do we care about doing this? As I just mentioned, it makes the tool available for everyone. So I think everyone realizes that right now, the state of Haskell tooling, there's a huge amount of dependence between GHC and all the subsequent tooling. All the tooling basically uses GHC as a library to get things like the abstract syntax tree, etc. And this is great because people get a lot of things for free, but it would also be great if there was a way to decouple these two things and make these things available to people who don't want to actually tap into GHC as a library. And then the other benefit is generally just to let people take advantage of this new motion to represent errors as structured values. So for those of you who are GHC contributors, you might be familiar with what this means, but just to touch on it very briefly, in the old versions of GHC, errors basically used to get passed around as a type called sdocs, which you can really just think about as strings. Essentially, at the call site, a string was produced that described the error, and then it got passed up, which is very easy, to just do and make new errors willy-nilly whenever you want. But it creates a big problem for actually creating sophisticated Haskell language tools, right? Because that means a lot of people are having to parse these strings by hand to figure out things like which variable triggered this issue, et cetera. So basically, we want to make these errors as useful to people as possible. And so there's been this motion underway to represent errors as structured values, basically. So you can think about that basically like instead of passing a string around, you've got a sum type that represents all the different possible error cases, and each one has its own constructor whose parameters are the values of note, basically, in the actual error. So just to give you an example of what it looks like now, this is like almost all of the code I actually have in this presentation. But so this is the current implementation of errors in GHC now with this new errors as values paradigm. And the details don't really matter. This particular E here is something that generally is going to be an instance of type diagnostic, which is this class. So basically you can see now getting passed around all throughout the compiler is all of this information separated out, right? You can separately grab diagnostic codes, the diagnostic reason, the message. All of these individual pieces of information are not just one single string, but are available to people who are actually tapping into GHC as an API. So now that you see that, it maybe becomes a little bit more apparent why there's a benefit to actually expressing these constructs in something other than GHC's API. We want to make them available to people who don't want to have to tap into GHC's API and instead just make them available to anyone that wants to write a tool in any language, whether it's Python or JavaScript or anything. So just a quick acknowledgement. There is actually a flag in GHC right now that does more or less do something similar. Maybe it looks familiar to some of you. It's this dedump JSON. And this flag is useful, but its usefulness is actually quite limited as it stands right now. So on the one hand, the way things stand right now is it's a little underspecified. So you can actually look at some of these details and you see that you're getting the same JSON structure out for a compiling message and also for a diagnostic message when these are clearly two different things. Additionally, you can see that in the message class field right here, there's a ton of good information, right? I mean, it's got the error code, it's got the message class, it's got the severity of the error, and it also has this just parameter. What does that mean? I'm not sure. But the point is, if it's not obvious to me that's been working on this, it's definitely not obvious to someone who's been working on the code base trying to develop tools. So how can we make this info more easily grabbable, more obvious what it does? So how do we do that? There's a new flag, fdiagnostics as JSON, that basically produces all of the error messages as single lines of diagnostic messages represented in JSON. And then additionally, we have a JSON schema that basically formalizes the exact contract of what you can expect to come out from each of these diagnostics. So this schema is really an important thing because it makes it explicit to users what exactly they can expect to come out of this flag. So JSON schemas is a particular concept that maybe not everyone's familiar with. I don't want to spend too much time on it, but it's kind of what it sounds like. We want a way to basically inform users that there's some constraints that all of these outputs are going to satisfy. And so this is extremely useful because it lets people expect consistent outputs from GHC, and when there's a change, they can actually go check the schema to understand the change that's been made. So we'll see an example here of a little bit of a JSON schema, but if you're actually interested in learning more about it, it's here. It's got lots of different bits of, like nomenclature and whatever, but the details aren't important. the idea is really just this, right? If you are a developer of a GHC tool, now you can look at this schema and see, oh, I know that only warning or error will be reported in the severity field. And I know that codes can be null or can be integers. And the reason why they can't be null is a variety of reasons. Some errors don't have integers assigned yet, and some errors are the result of plugins. But regardless, now you can make much more informed decisions about what you can actually expect to come out of this diagnostic message. So the current state of things is that there's a merge request open. I think it looks okay. I've actually gotten some feedback from some people in the audience here, which I appreciate a lot. But it's not merged in, and I think that there probably are people here that would benefit from such a feature. And so if you are one of those people, now, or I guess not like right now, but now in a general sense is a great time to give any feedback at all about things that you wish it had, things that you wish it didn't have, etc. So the flag is fdiagnostics as JSON. This is what error messages look like now, and here's what they look like with the flag passed in. It got a little cut off, but I think you understand the spirit of the message. And possible work down the line. Rust's compiler actually also has a JSON output feature, but the difference there is that theirs is actually a little bit more sophisticated and also offers JSON output of all different kinds of output. So compiler messages in addition to actual diagnostic messages. That could be a useful thing down the line, but that would involve a new specification, and so I was trying to keep the scope limited. And then we can also, of course, add more useful information to the JSON diagnostic messages. So yeah, that's my presentation. Happy to take any questions or anything like that. And again, please reach out if you actually have things that you want changed about the flag. It's not merged in. Everyone knows it's much easier to do things right the first time than to fix things after the fact. Yeah, and also just thanks to Aaron Allen for mentoring me through this and the Haskell Foundation for doing this program. Thank you, everyone. All right.
Dominique, are you ready?
Hi, everyone. My name is Dominic Millshowell, and I'm going to talk about the work I've been doing in Summer of Haskell over the past couple of months, specifically with the Improving Calligraphy project. So you're probably, the initial question in your head is probably, what's calligraphy? So calligraphy is a Haskell call graph / source code visualizer. It uses information from the HIE files generated from GHC to produce visualizations. And for the uninitiated, HIE stands for Haskell Interface Extension. They're binary data that's produced from GHC during the build process, and it contains serializable data related to Haskell modules such as type information, metadata, and the like. And this is very useful for developing tooling, more advanced tooling with features such as navigation, code completion, and the like as well. So the benefits of this is manifold. And it's probably the most prominent use of HIE files is within the Haskell language server. And to kind of give you a clue as to how calligraphy looks like in its formative stages, this is how I got it handed to me. It's after building with Cabal and getting executable and then adding it to your path, you can target specific modules and it would produce a neat graph like this. Of course, if you don't add any arguments related to specific modules, it would just generate a graph containing all the modules within this project that you specified. And some commentary is necessary here. So the house-shaped nodes are type classes. The octagonal node is a type constructor or type family or type synonym. The rectangle is, oh, I'm sorry, I got ahead of myself. So, all right, this repository is from Edward Kemet's semigroups library. And the reason I chose that specifically with these two modules is because those encompass the entire possible nodes that calligraphy uses and also all the possible edges that calligraphy uses. So it serves as a good motivating example to explain everything that, it's an exhaustive example, as you could say. And as previously mentioned, the house node is a type class, the octagonal node is a type constructor, the rectangular node is just a regular constructor, the ovals are just values. The rectangular node with the rounded edges are records, and the ovals are just values. And the arrows, there are three types of arrows. There are the solid line arrows, which indicates a relationship from a caller to a callee, meaning that where the end of the arrow was called in the beginning of the arrow, and the perforated lines indicate a parent-child relationship wherein what's usually on top is the parent and what's usually on the bottom is the child. Parent and child here means that the child was introduced somewhere within the body of the parent. And I mean, I know this sounds quite general in a sense, but it's best I describe it this way because it does encompass different types of situations. And for the sake of brevity, it's better not to go into this. But also the dotted lines also indicate typing relationships. So what was used in the type at the end of the dotted line, what's at the end of the dotted line arrow was used in the type of the initial starting point arrow. So from the get-go, if you look at something like this, you can see, yeah, it's really useful if you want some information about whatever Haskell project you're working on, but also it's not very interactive. If you have a really huge, large-scale project, it's going to generate this monster of an image in which you really can't discern what's going on. And it would benefit from having some more interactivity. So the goals of this project were twofold. One is to modularize calligraphy into various parts, such as the calligraphy GUI, GraphViz, CLI, and FGL. So FGL is functional graph library. GraphViz is a means to generate graphic type data. And the second point is to ensure that calligraphy keeps up to date with new GHC releases. So I'm going to tackle the second point first. And if anyone's ever maintained a Haskell project or kind of delved into one, you'll notice that it's kind of a struggle to just keep up to date with new GHC releases. You usually have to kind of use some hacky method where you introduce some snippet that says if this GHC version is available, if you're using this current GHC version, then this snippet applies, else this snippet applies. And we need a more sustainable way to kind of address these new changes. And I'm sorry to say that I did not achieve this because GHC is kind of a complex beast. So after spending an inordinate amount of time on this, I've kind of redefined this goal as more of a stretch goal. But funnily enough, I have actually gotten a lot of insight from just attending the symposium. So, I mean, I've gotten a lot of different perspectives, such as like using bidirectional programming, template metaprogramming, and even I hear there's work being done on an API to kind of consolidate various different, differences between different GHC versions. But of course, this is, in its infancy, and it hasn't really reached a point of fruition yet. But the goal itself was, I could say, in a sense, unachievable because of just the complex nature of GHC. But I kind of just want to still talk about some of the issues that are present within the code base now related to this issue that I'm mentioning. So, if you look at the type-related logic, meaning the logic that I just described to this, like how the various edges and nodes are formed, then it's not that much. If you look in the repository, it's just 15 lines of code. And it works in general pretty well, except for some particular exceptions, such as with field accessors in GHC 9.2. And what we usually what we have done is just kind of take an approach where if it works, it works. If it doesn't, it doesn't. Because if it works 90% of the time and it doesn't work 10% of the time, then we're not really going to focus on the 10%. We're going to just focus on the 90%. And another issue is just that it builds with the most recent versions of GHC, but it can't necessarily parse and handle all the call graphs generated from all the GHC versions. Sometimes calligraphy will be nice and error out. Other times, you may just get an incorrect call graph returned. And this is just kind of an overview of my struggles with trying to just work with different approaches to deal with these GHC, these versioning issues. But realistically, it wasn't necessarily feasible to come up with this, so I'm going to talk about the more productive option of the two, which is modularizing calligraphy. So this was the initial goal, to kind of modularize calligraphy into various constituent parts. And the reason for this was hinted at before, where it's unwieldy to just use a CLI. You kind of want something more interactive, and you want something more maintainable if you want to add. Well, also you want to add certain kind of bindings, because right now the logic used for GraphViz and FGL is ad hoc. It doesn't actually delve into the libraries themselves, but rather just particular use cases of what we need to generate a graph that we want. And the issue, as I just said a while ago, the issue lies with designing the GUI currently. So this is not so much an engineering problem as it is a design problem, because we've taken maybe 3 approaches. So one using D3.js, which is the JavaScript library for producing nice visualizations. This works, but it's not very maintainable because JavaScript. And we've also taken an approach using PureScript, which is maintainable but not useful for kind of just coming up with things on the fly, which is, if you want to move fast, I've taken the approach of using GTK+, which works well if you just want to break things fast and figure out why they broke and then try to fix them. And the reason why the graph configuration is kind of challenging is because the design space is quite large. And what I mean by that is that it's large in the sense that if you have a large project, it's going to be large because you generate so many different configurations of disjoint graphs. But also, it's large because the tools that we're using are somewhat underspecified for more complex cases. And that's where the aspects of GraphViz and FGL come in. Because how calligraphy works right now is that it builds the GraphViz file by just concatenating text in a very ad hoc fashion, instead of relying on like a more complete solution. So if you want, something more refined, you're going to have to write it yourself and get calligraphy to build it. So in the similar vein, if you want more nuanced algorithms or if you want something like, say, the boundary of a graph, you would probably you can't get that from the get-go with calligraphy. It'd be much better if we have a more general approach that integrates the FGL library. And the upshot of this lightweight approach is that it works, it's simple, but for future use cases, it's better to kind of just have those bindings in place so you can have far more options available to you. So in terms of the work being done, which I probably didn't categorize as in this talk as it would, the CLI is complete, and more or less the bindings have been in place. The issue mainly lies with the GUI, and I actually really struggled to put the GUI on a slide because it's just so unwieldy. Like, you don't really see anything. You just kind of see some dots that you can vaguely make out. So it didn't really seem necessary. Well, I couldn't figure out a way to put it on the slides themselves. And yeah, that's more or less where we're at. So thanks for your attention.
Greg, you ready?
Okay, this, I'll just hold it, I guess. Sorry. Okay, hello everyone, I am Greg. My project is maximally decoupling Haddock and GHC. A bit about me is that I am currently a university student. This is a project that I did. This is my summer project, basically sort of like a summer internship, I guess. Wait. Anyway, so the background for this project: GHC is the compiler for the standard compiler for Haskell. There are others, but this one is pretty much the de facto standard. Likewise, Haddock is the documentation generator for Haskell, which takes a Haskell project and outputs documentation in various formats. One format would be documentation that you can view on Hackage, the package manager, which you can view online. Another format would be for another backend would be for Hoogle, which allows you to search for functions via names or type signatures. And the problem is that these two tools have a very large, is that GHC and Haddock have a very strong connection between each other. Haddock is strongly coupled to GHC. For instance, the Haskell abstract syntax tree is defined in GHC and used by Haddock. And this is unfortunate. This is largely out of necessity in a way because GHC's syntax tree is very large. It is very unwieldy. However, this is a problem. The abstract syntax tree changes quite frequently, relatively frequently. Every time that, for example, that there is a new language extension, it is often added to the syntax tree. There's also refactoring done internally in GHC for other reasons, and every time that this happens, the types of the syntax tree change, and likewise, and so Haddock has to be changed as well. What problems does this cause? What problems does this linkage cause? For one thing, this means that the version of Haddock that you use is tied to the version of GHC that you're using. This presents a major problem, for example, for tooling such as Hackage, which struggles due to the gap between Haddock versions and GHC versions, and the large number of GHC versions that are used by packages on Haddock. Some packages are very new, while others may be years or decades old. Another problem is that the development of both GHC and Haddock is slowed due to the need to make sure that both of them are using the same version of the AST. And my proposal for fixing this issue was part of a larger effort to decouple Haddock and GHC, and I proposed the following steps. One of them was designing an intermediate. I proposed these following steps as part of my project. One was to design an intermediate representation, IR, for the Haskell AST, and implementing the conversions between the AST and the IR, and serialization to and deserialization from disk. Another necessary part was to of course update Haddock and update GHC to interact through the intermediate representation rather than directly sharing the syntax, and then having Haddock get the syntax tree directly from GHC. And another change was to, of course, update the Haddock backends, which currently use the Haskell syntax tree from GHC in order to use a representation which is not imported from GHC. Can read more about this in Haskell Tech Proposal number 44, I believe. And you might ask, why do we need a new intermediate representation? Why not simply use the Haskell syntax that we already have? You can already, of course, serialize it to disk, deserialize it by parsing, and you wouldn't need a conversion. And to answer, and I mentioned this because I think it's good to it's good to understand why this would be helpful. And one reason is towards compatibility. If you know, future Haskell versions may have new syntax, and they probably will introduce new syntax that is currently unsupported by Haskell, and this of course is a problem. If you tried to parse a modern Haskell project that makes use of some language extensions which introduce new syntax using a much older version of GHC, you would get a parsing error. However, with an intermediate representation, you could enforce a consistent syntax, allowing the parser to at least parse the project, and of course, some parts would nonetheless have the new bits of syntax, new features which are unsupported by the current version of Haddock. But with those you would be able to identify them and minimize the scope of the impact, perhaps outputting most of all of the bits of documentation you can, except for the very few pieces that depend on those new features. As another advantage is being able to interact with third-party tooling. So a lot of tools may be written that may want to make use of Haskell AST, and not all of them may necessarily be written in Haskell. Some may, for example, be written in Python. These obviously cannot make use of any Haskell libraries for dealing with the Haskell AST. They probably do not have a Haskell parser available. And of course, writing a Haskell parser is especially for a small tool, is going to be very undesirable. Parsing Haskell is currently rather complex, and you don't want to go through all that trouble. Instead, you may use an intermediate representation may be designed so that it is much easier to parse. And in fact, depending on the intermediate representation which is chosen, a parser may be available, quote unquote, out of the box. This brings us to the chosen intermediate representation. It is basically JSON, and this has a few advantages. One is of course that JSON parsers are available out of the box for many languages. Instead of having to write so if you wanted to write, for example, Python tooling to work with Haskell code, you would not have to write a parser. You would simply have to parse the intermediate representation as JSON, and then depending on the language, you could either use the parse result as is, or write some boilerplate to convert it into a statically typed format if you are using a statically typed language. Another advantage of JSON, more so of a requirement really, is that it supports all the features that you would need in order to adequately represent Haskell code. It has strings, it has numbers for primitives, and JSON arrays and objects provide a convenient mechanism for representing Haskell structures. Features such as records and different constructors in the cases of some types may be encoded through the use of a special label that may be specified in the schema. And so during the work on this project, if we go back, we can see that the original proposal was quite ambitious. Unfortunately, not everything could be accomplished due to several setbacks. One, for example, is the way interoperation between Haddock and GHC works. Haddock, as it currently is, essentially uses a GHC plugin. It goes into, and what this plugin does, it's a rather complex thing. It goes into GHC and it not only extracts the syntax tree, but also does some processing on it. And I felt that replacing this plugin would be a technically difficult project, perhaps requiring additional feedback. And so I decided to move this to future work in a way on commentary. Another issue is the broader effort to remove the Haskell AST from GHC. This is currently an ongoing effort. There is work on moving the Haskell syntax tree into a module language.haskell.syntax, which is not part of the quote-unquote GHC core that is problematic to use in Haddock. However, this project is ongoing. Some parts of if you were to actually use language.haskell.syntax, you'd find that there will be some dependencies that are still in core GHC. So unfortunately, as it is, this fully moving away from GHC in the backends cannot be done yet. You may ask why, and of course, why not simply copy the syntax tree? The answer is that, again, it is very large, very complex. You do not want to do this. And ultimately, the final product of this project will be a proposal, which will include the intermediate representation, a prototype which accomplishes conversion between the Haskell AST and the intermediate representation, and of course serialization to and deserialization from disk. This prototype, of course, will not necessarily be suitable for use directly in GHC. It is entirely possible that there will need to be refactoring and optimization done in order to use it. But the point is that it will serve as a demonstration that that the intermediate representation does work. There will also be indication of future work that needs to be done. For example, the steps needed to fully integrate this into Haddock and GHC, and of course, room for commentary on how these steps can be taken. And hopefully, the work product of the project may be used to improve Haddock and GHC. That this proposal should be available in a few weeks, and that would be a perfect time to leave comments on it. And as for acknowledgements, there was already a table of mentors and participants and mentors, but I would like to acknowledge my project mentor, Laron, and the Haskell.org committee for making Summer of Haskell possible. Thank you.
All right, thanks. So next up, I'm going to play a couple of videos from people who weren't able to make it today.
Hello everyone, I'm Suganya Raju. I'm going to present on structured errors and error codes in Cabal install, which I'm working on as part of Summer of Haskell under the mentorship of Gershom Besaman. Unfortunately, I couldn't attend this event in person, but I'm glad to have this talk virtually. To begin with, I would like to start with the motivation behind this work. The Haskell error index describes various messages that can be returned by Haskell-related tools, including both errors and warnings. For example, GHC started emitting a code with the format GHC followed by a unique numeric code for its error messages starting from version 9.6.1. So far, 102 errors and warnings are documented here. These codes can be looked up in the Haskell error index site for further information. Such a centralized error index works better when more Haskell tools participate. So the aim of this project is to integrate errors in Cabal install with the error index so that they can be centralized and documented as well. In the same vein as GHC and Stack, this project is to refactor the Cabal code base to provide structured errors rather than mere strings. So why is there a need for structured errors? An oft-repeated challenge in learning Haskell is the quality of error messages, especially for beginners like me. For example, an error message may have an unknown provenance, whether is it generated by Stack or by Cabal or by GHC or by Haddock. An error message may mention concepts unfamiliar to the programmer or unrelated to the problem. Sometimes they contain too little information. These kinds of problems can be solved by having structured errors. For example, if a programmer runs into an error and the error message is prefixed with a code in the format Cabal followed by a numeric code, it can be easily understood that the error is in the Cabal tool, and the numeric code can be looked up in the index to understand better. Thus, it helps in categorizing the errors into its respective Haskell tool, and new users don't have to figure out which tool is the source of the error. And this will eventually lead the users to have an easier time contributing documentation for how to work around various situations that may arise. So what will be the outcome of this project? The idea of the project is to have one data constructor per error and create a data type for exceptions that have specific constructors for each one and is incrementally added to. Along with this, there is a display instance that turns it into a string to emit and an associated numeric code for each constructor. Then at the top level, the handler that catches and emits exceptions will format the numeric code and the string all at once. So our end goal is to have a package-specific error data types where each constructor of such a data type will represent one error corresponding to the error that the module can throw. With respect to the existing error infrastructure, currently Cabal usually terminates with an error through calling the die- function. This die- function takes a verbosity, an error string, and throws an exception that just wraps up the error string, and the call stack information is already rendered within it. In order to have structured errors, there are a few core changes we have done to the existing infrastructure. The first one is the introduction of two new sum types. One for Cabal package, that is Cabal exception, and the other for Cabal install package, which is going to be Cabal install exception. Second change is a creation of one more data type named verbose exception, which will be a wrapper for data types Cabal exception and Cabal install exception, and it will also capture the call stack and the verbosity. The third is an introduction of a new function, die with exception, which will be polymorphic over exception types and will replace the die- function in all of its occurrences in the Cabal code base. And this is how it looks when the exception is instantiated. Each error message is assigned a unique code of the form Cabal, followed by a unique numeric code, and rendered along with the metadata at the display time of exception. Here, I have taken a small part of the module in the Cabal package to reference. As you can see the difference in the proposed design, the die- function is replaced with the function die with exception, which takes in the verbosity and the exception it is supposed to throw. After this, the exception is caught and pattern matched to retrieve the error code and the error message accordingly. So once this executes, this is how the new error output with the error code is going to look like. As you can see, there is error followed by the cabal and the numeric code. This is a screenshot of the Haskell error index, which has errors from GHC and stack for now. The error code that we have generated as part of this project will be added to the existing error index, just like the way it is shown here. Once this is done, users will be able to read about why an error occurs and the cause for the same. And that's the end of my talk. Thanks to my mentor, Gresham Baserman, and the Haskell community for their support, guidance, and this opportunity. Thank you. I'm going to present on errors and error codes in Cabal instance.
Sorry about that.
Hello everyone, my name is Nathan Maxson, and I'm one of the students for this year's Haskell Summer of Code. So let me introduce myself. I started programming when I was young. I started with PHP. Later I did some Python, some Java, and then learned a bit about Scala and Haskell. However, for university, I studied teaching Chinese to foreigners. Later, I worked teaching English and translating. Eventually, though, I decided I would like to go back to programming for a living. So, toward that end, I applied to this year's Summer of Haskell. Disclaimer about this project. What I was working on was the interaction between the HLS server and the LSP client. So there were no significant user-facing parts to this project, so that means no screenshots or fancy videos. Let me give you a little bit of a background behind the project. The first work to support Resolve was done by Zubin Dugal from WellTyped, and he added Resolve to completion items, or support for completion items / Resolve to HLS, and this allowed him to delay the computation of the documentation and types field for completion items and provided significant performance improvements. But my project was to follow up on his project and add Resolve for code actions and code lenses, as well as to go and make Resolve easier for plugins to use. So let's talk a little bit about what Resolve is. For those who don't know, LSP is Language Server Protocol. We define specific methods that allow the client, like Emacs or VS Code, to request information about a code file from the server, in this case, HLS. One method, for example, is called text document / code lens. It's a request to return a list of code lenses for the whole document. If we're not using Resolve, we need to compute the title and return that along with a range for each lens. However, when we are using Resolve, we can instead just return a range for each code lens. And when they come into view, the client will send us a request for the title. This allows us to delay the computation of the title. So Resolve is not just for code lenses. We have Resolve for code lenses, for completion items, for code actions, among many other methods. But what we can resolve for each method is different. So code lenses allow us to go and resolve the title. Code actions allow us to resolve the edit. Completion items allow us to resolve the documentation fields. So let me give you a little bit of an overview of what my project entailed. For those of you who don't know, previously LSP types, the package, was handwritten, and because of that, it would always lag features compared to the latest LSP spec. but Michael made a new version of the LSP types package, which was generated. So we had all of the types from the LSP spec, and we could always stay up to date. The only problem was that this wasn't implemented in HLS yet. The new package wasn't supported in HLS yet. So this was my first part of the project. It was intense, but it was also educative, as I had to go over every part of HLS. Many of the changes were small, and for those, Haskell's easy refactoring really came into play, as most of the time I could follow the types and see where that led. There were a few tricky problems. There were some bugs in the LSP types package because HLS was the first user of the new version, and those bugs I had to fix. But in the end, I made up about 5,000 changes, and it touched around 194 files. So after that, I ended up implementing resolve in HLS itself. A naive implementation of resolve methods in HLS is pretty simple because HLS doesn't really need to know very much about the methods that the LSP client sends. But in addition to general support, I also added some quality of life improvements, allowing plugins to have an easier life supporting resolve. So one example of that, the quality of life improvement, is that we automatically deserialize the generic JSON data field that we get to the handler specified argument type. So we'll talk a little bit more about that later. And for some of the methods, they only supported resolve relatively recently, for example, for code actions. And we still want to support older clients that don't support resolve. And where one option would be have every plugin check what the client supports and then change your behavior depending on that, we instead opted to go with a method where we actually dynamically rewrite the plugin's response depending on whether the client actually supports resolve or not. And that allows the plugin to go and be completely ignorant of whether the client supports resolve or not, and allow it to have a lot less code and more cleaner code. I also implemented resolve in 7 plugins. Part of that was understanding what would be the best way to implement resolve in HLS. Along the way, I also solved or fixed several bugs. So some of the bugs I fixed, preventing exception in commands from taking down the whole server. Commands are the type of request that we get in HLS. I fixed a Pragma plugin from offering incorrect code actions for HNet diagnostics. I fixed explicit record fields from offering duplicate code actions when inside a HS expanded clause, which is like what we use for new JC features. And sorry, one second. And I also merged the explicit imports and refined imports plugin that ended up removing a lot of duplicated code. I was also able to work on some HLS projects that weren't strictly related to my main Haskell Summer of Code project. So one of them was making a significant improvement in the JC GHCID code base and allowing us to have much cleaner code base and moving towards where we can turn on WErr for GCID. We already turn on WErr for GCID, but we have to make certain exceptions. So we have to cut down significantly on the amount of exceptions we had to make, and I left behind a much cleaner code base. The next thing I did was actually building off another member of the Haskell language servers, Fender's work. He had started, but he didn't have time to finish. So I took up his project and I did some changes to it. The project was changing how plugins handle errors, a rather large change to how plugins handle errors. And previously, every plugin would respond with a LSP response error, but that didn't work very well because there's no easy way to combine them. But we came up with a consistent way that plugins could have plugin-specific errors that they could respond with. And all plugin responses are now crafted in the except T monad, which allows us to throw errors and short circuit the rest of the code easily. In addition, we have a bunch of commonly used functions that also throw the right error if they fail, which is, we have good failures and we have bad failures, and this allows us to know exactly what's happening inside a plugin. So let's go and take a look at what Resolve looks like in HLS right now. This is an actionable example of Resolve in the HLN plugin. So let's start with the type, Resolve function, ID, state, HLN Resolve commands, method, code action, Resolve. This is a type synonym because the actual type is quite long. So it's a function that takes ID, state, plugin ID, code action, URI, HLN Resolve command, and is executed in the except T monad. So a lot of these are actually pretty standard for all Resolve handlers. ID state is, plugin ID is, code action would be considered the parameters for the request. The URI is helpful because we always need the URI when you do pretty much anything in HLS. HLN Resolve command is what we extract from the code actions data field, and we deserialize it for this Resolve handler. And if you're unable to deserialize the data field to HLN Resolve command, then we won't call this Resolve handler. So if you remember from before, every request has different parts of fields rather. They can be resolved, and for code actions, we can resolve the edit field. So here we're returning the code action with the edit field replaced with the edit that we computed. I would like to especially thank my mentor, Michael, for his guidance through my project. He was awesome. In addition, I'd like to thank the Haskell Foundation and all Haskell Summer of Code sponsors for providing me this opportunity to spend the summer improving HLS. Thank you all.
We're going to swap the computers now.
Hello? Okay. Too close. All right. Working? Showing my screen. All right. I hope I'm audible. Yeah. Cool. So, good afternoon. I'm Sachi, and I've worked on a project called Tidal and Mandalas, and I've done it under the researcher Alex McLean at Then Try This. All right. So, some background. I was in a women engineers program in India, and that's where I was introduced to Haskell around 2 years ago. But I did not start taking it seriously up until December of last year, wherein I did a project in it, one of my first bigger projects. So that was called PAIP Goes Haskell. Paradigms of Artificial Intelligence Programming is a book by Peter Norvig. It's about classical AI programs from before the 90s, so about programs pre-neural networks essentially. And the programs in it are written in Lisp, and we converted it into Haskell and Golang. I specifically worked on the Haskell part. And I learned a lot here, but I wanted to do larger projects. So I saw that Summer of Haskell was accepting applications and beginners were encouraged. And additionally, I saw that in my project, last year the contributor was also an Indian student, so that encouraged me a lot. So this is my project. My proposal was to produce beautiful visualizations in Tidal Cycles, the platform for live coding, using, to produce mandala visualizations. What are mandalas? They are repeated geometric patterns formed by circles, squares, and these combine in specific manners to produce these visualizations. They are fairly common in Southeast Asian art, and but they are generalized to an extent that they can be used in many different places and are fairly common now. So what is Tidal Cycles? Tidal Cycles is a live coding environment for producing music, and it has a mini notation that is essentially a DSL built on top of Haskell. So you take snippets of music, like suppose BD over there is a bass drum, a snare drum, and then you apply functions on it. You compose these functions to produce music. So I'll just show an example. Will it load? Yeah. This is a clip of somebody producing music. It's not audible, is it? Great. Fantastic. But is it?
You need to.
Yeah, I need to connect this.
There you go.
All right. Still not working? All right, great. I'm going to try to play this.
This is connected.
This?
Yeah, it's this one.
Yeah. Sorry.
This is connected. Sorry about that.
Okay, this is not. Yeah, it's not. Okay, it's all right. I'll just continue. We can show this later also. Right. So it produces music with functions. The problem, as you could see, were visualizations. If you saw the first clip, they were just notes moving forward with time, nothing special. So I thought that since all these functions will work on underlying structures, those can be used to make mandala-like patterns. So initially I thought, okay, let's go to the basics. I thought about when I was in 6th grade, I used Microsoft Visual Logo to make circles and squares, and I thought, okay, we can use that. So a logo-like system to produce graphics and basic notation, move forward, move right, move left. And the library I used was WorldTurtle, which is built on top of Gloss. This is an overall overview of my approach, but it's a basic approach. Initially, I tried to explore Tidal, saw what functions it had. Then for a while, I explored what animation libraries I could use. And additionally, I also did some more research on mandalas. I created a basic total notation in Haskell. And after that, I integrated that with Tidal's parser in order to produce the turtle notation values. And I also integrated it with WorldTurtle to produce the total notations can produce the animations. But there was a problem. my system's not real time. So I was taking a pattern and I was just querying it for like, okay, 400 seconds, give me all the values. But at a particular point in time, I did not know what value to take. So I went a level lower to gloss and tried to explore whether this would be possible. And that's where I am at right now. I'm working on that. So let's do a demo. All right. So I would first like to go bigger. Yeah, 1. So if we look at some basic patterns, for example, let's go forward. It goes forward, great. But if we go, okay, that's making a square. What's that doing? That pattern goes F and then R. So in the first half of the cycle, it goes forward, and in the second half of the cycle, it goes by a factor of 90 to the right. And this is proportional to the time in which the pattern is active. That's over there. So the first half, it goes forward, second half, it goes right. This is proportional to the time. All right, let's go. Let's try something else. All right, we're getting different shapes over here. That's working, that's doing something else different because the time for which the pattern is active changes. All right. Okay, so now we'll go to some mini notation stuff. So these are different ways in which the mini notation manipulates the pattern. So, okay, it goes forward, goes left, right, forward, forever. Not forever, for the cycles. And at this point, we start seeing some interesting things. This is making a spiral sort of structure, and yeah, it'll go on for a while, but that's what it's doing. All right, and finally, but this is just manipulation with the mini notation. The title has additional functions also. So, yeah, these are just 2 of the functions, fast and slow. Fast speedens the pattern and slow slows it down. So if you go for the first one, okay, that's the second one is doing. But you can slow it down by a particular pattern also. So the value it is using, this is producing the second one, is slowing it down by the Fibonacci series till like 1 through 8. And as you can see, it's doing something very strange. I don't know what that is either. So these are some of the patterns that I have produced. This pattern produces this weird spiral looking thing. We have this festival called Diwali where we make rangolis on the ground. They look kind of like this. I like to call this one a ninja star with like some clan that it's really hot in their area, so they need a fan. And this one is what that pattern is. So it goes in all these different weird directions and comes back to its original spot. And I think it's symmetric along some axis, but I'm not entirely sure which one. And my friend who likes physics told me it looks like Brownian motion, and I was just thrilled by that. So yeah. What are my learnings from this project? The 2 main ones are thinking in different programming paradigms. So I love working with Haskell. I think it's a beautiful language, and it allows me to think differently at a different level of abstraction. And additionally, I saw how different fields were interconnected visually. Like I was able to see that rather than just abstractly think about it. So obviously these musical patterns producing different kinds of patterns. And yeah, even the comment about Brownian motion, like I just thought, it was beautiful to see that. So finally, the future scope of this project includes, Tidal has a new version coming out, so I want to integrate with that version. Additionally, I saw that L systems can be produced using Turtle graphics, and I wanted to see if these can be produced with this framework. There's a problem because Tidal doesn't really use state that well, but we'll figure it out. And I have to deploy my project on Hackage. So again, these are the links to the repository. Thank you to the Haskell Foundation, Haskell.org, for sponsoring this project. It's been a great time, and my mentor, obviously, Alex McLean, for mentoring me through these months. Thank you.
Our presenter waiting on Zoom. Can we switch to Zoom?
Hi, I'm Elodie Lander, and I have been working on getting go-to definition in Haskell language server to work for external dependencies in a project. So I'm going to start with a live demonstration. So let me just share my screen. And okay, can you all see everything here? Okay, so can you see the launched VS Code here?
Yes.
Okay, great. All right, so here is a function that is not part of the project. And so I was able to go to definition. Once I have a dependency file open, hover works, and go to definition also works in here. Let's go to a different one. Let's go to the ASON. Yeah. And so then from here, I can go to another definition. And I can even go to transitive dependencies. That's not going to work. But we go back to this. And so we can go to internal dependencies. And so let's talk about a little bit how is this working. So you can see up here the file that is open right now. So we're putting this in a .hls directory inside of the project. So you have my sincerest apologies that if you're using Haskell language server and you start using this feature, you're going to have to add .hls to your gitignore. We talked about the possibility of opening these dependencies where they are. The Rust community is able to do this, but the way that they do it is just through the client, through VS Code, and we decided that that was interfering too much with how the language server protocol is intended to be. And we didn't want to do that, especially because we have support for multiple different clients. So we're opting for this, where we put inside HLS dependencies, and then this is essentially going to be the same name of the directory that you would see in the Cabal store. And then we have the Haskell file. So how does this work? So the first thing that we need for this to work is we need Cabal head. So the first thing that I did in this project is how do I move this? Oh, there we go. Is I made a small change to Cabal that allows it to copy HIE files into the Cabal store if the user has the fwrite IDE info GHC tag enabled in their Cabal configuration. So the most important line of code in this change is where we actually set the HIE dir flag. So this, oh, it's right here. Okay. So the HIE dir flag, this changes where HIE files get produced when the FRI IDE info flag is enabled. So what we opted for in this is to put it in a directory called extra compilation artifacts. This is a directory that Cabal was already producing for GHC plugins, and it already copies this directory when it's installing a package in the Cabal store, if it exists. So basically, just adding this directory in was the main thing that needed to happen for this change. So let me show you. Okay, so we're looking at dependent map, and this is that. So let's take a look at what the Cabal store looks like. So we've got dependent map, and this is 0.4.0.0 dash, and this is D. Yeah, okay, so if we look in here and in the lib directory, there's the extra compilation artifacts directory. And if we do tree on that, you can basically see this is the whole dependent map package, but with just HIE files instead of HS files. So this is what Cabal now produces, and this is what Haskell Language Server can now look for. So now let's take a look at the main pull requests in Haskell Language Server. So there's two main components to what makes this possible. So the first thing is, let's take a step back and talk a little bit about how GoToDefinition worked before. So essentially, Haskell Language Server, when you go to a definition, it's gonna grab the name of what you are going to, essentially from the HIE AST that it has, and then it's gonna try and load that up. And if it can't find it in its own environment, then it's gonna look in the HIE database. So there's a project called HIEDB, which is maintained by my mentor for this, Zubin Dougal. And HIEDB essentially is an SQLite database that has tables for the modules in a project, for example, and the units, the packages. And so the GoToDefinition code, when I came to it, was designed in such a way that it was intended that we would have GoToDefinition support for external dependencies at some point. So basically, I just needed to fill in the definition of lookup mod. You can see before the changes, it was a stub that was just returning nothing. But basically what this does is this file path here is an HIE file that we got from the database. So this is assuming that we already have indexed in the database all the HIE files that we need. And this is going to load up the HIE file, and basically all it does is get the raw byte string of the Haskell source from the HIE data type and write it out in the HLS/dependencies directory. There's a few more things that this does in terms of the database. So when we initially index an HIE file, we're not gonna have the source file in the database, in the SQLite database, because it doesn't exist yet. But when we actually get to this point where we have the HIE file, at this point we are going to register the Haskell source file that's in .hls/dependencies in the database. And that's the behavior that you just saw in Visual Studio Code. All of these are dependencies that I've brought up before. So this was essentially just looking, it never actually even made it to this code, right? It was just saying, oh, that Haskell source is in the database and we can just bring it up, and that file already existed, I'm pretty sure. So the other main component of this functionality is in a new file, which is called, core dependencies. And this is where all the indexing happens. So this grabs data from GHC. So there's a data type in the GHC API called an HSC-env. And that has all kinds of information about what packages are available to the compiler as it's building our libraries. So the main function here is index dependency HIE files. And this gets called every time a new HSC-env gets loaded up by Haskell language server. So essentially what we're doing here is we're grabbing all the dependencies from the HSC-env. We're filtering them using this function, calculate transitive dependencies, to make sure that we're only getting things that are dependencies and transitive dependencies. And then we are sending them off to the function that already existed for indexing an HIE file in the HIEDB database. So that function, well, I don't think I need to get too into details about how that works, but so all of this stuff gets put into the database. And then once we call go to definition, then it's just, if the Haskell source file has not been written out yet, then we can just look in the database and it should be there. And then we can write out the file and open it up in the editor. So what are the limitations of this? So the first thing is you need to have a recent enough version of Cabal installed. And we don't currently have support for libraries that are bundled with GHC to be indexed. So let's take a look at that. This is a patch that is to be merged in GHC, specifically in the Hadrian build system, that will basically mimic the functionality of what we did in Cabal, where we're going to have an extra compilation artifacts directory with all of the HIE files, and we're going to enable fwrite IDE info so that GHC is going to produce the HIE files for all of those directories. So as an example, currently, if I try and go to the definition of just, for example, just is defined in base. It's packaged with GHC, so we don't currently have the support for that, right? This is going to need a little bit more work still also because, so this will make the HIE files in a subdirectory of the build directory, the Hadrian build directory, called libraries. And what actually gets put into a binary distribution is another subdirectory called lib. And I believe at this point that cabal copy is what moves currently HI files and like dyn HI files from the libraries directory to the lib directory. So I think there's one more change that will need to be made in cabal to get this to essentially package up the HIE files that for all of the packages that go with GHC in much the same way that cabal will be installing them in the cabal store. Another thing that there's another potential pitfall that users could run into where, so say you've been working with Haskell language server with an older version of cabal, and then you get the latest code and you want to try out go to definition for a dependency. And so you upgrade your cabal, but say you already had FRI IDE info enabled. So the hash that goes into the cabal store directory and also the HLS dependencies directory, that, as I understand it, includes all the GHC flags, but it does not include the version of cabal that you used. So it's possible that you could have built your dependency with the FRI IDE info flag, but an older version of cabal, and so you have the same hash here in the directory, but you don't have the HIE files. So in this case, I still need to make an error that will give the user a warning that says, hey, it looks like you are missing some HIE files that we're expecting to find, and suggest that they maybe nuke their cabal store and rebuild everything. So the cabal pull request was merged a couple months ago. Still working on getting the Haskell language server PR merged. I'm expecting that will happen in the next couple of weeks. And same thing with the GHC patch. So I think that's about it. Does anyone have any questions? Oh, I'd just like to thank everyone who has commented on my PRs and given feedback, and of course, my mentor, Zubin, who has brought a real depth of knowledge from both Haskell language server and GHC to help point me in the right direction at a bunch of different junctures in this. So, and thank you to the Haskell.org committee for sponsoring this project.
All right, thank you. All right, that's everybody. And thanks to the contributors, that was fantastic. And looking forward to next year.